Master's theorem. Using recurrence relations. Let us know how recurrence relations help us analyze the running time of recursive algorithms. Using Master's theorem, we can solve these recurrences quickly and easily. What is a recurrence relation? A recurrence relation expresses the time complexity of a problem in terms of the time complexity of smaller subproblems. Examples: T of n is equal to T of n by 2 plus n. T of n is equal to 4T of n by 3 plus n square. Used mainly in divide and conquer algorithms. Why use Master's theorem? Used for analyzing divide and conquer algorithms. Helps determine asymptotic time complexity. Gives direct solution without expansion. Need for Master's theorem. Expanding recurrences is difficult. Master's theorem gives a direct formula. Works for recurrences of the form of n is equal to n divided by b plus of n, where a is equal to number of subproblems, b is equal to size reduction factor, f n is equal to extra work done outside recursion. Master's theorem format. Standard form of n is equal to n divided by b plus f of n. Function form. F of n is equal to n power k into log power p into n. Master's theorem compares f, n, with n power log base b into a. Case 1. This case occurs when the number of subproblems is greater than the amount of work done at each level. The recursive calls dominate the total running time. So, the overall time complexity is decided mainly by how many subproblems are created. Case 2. This case occurs when the number of subproblems and the work done at each level are balanced. Both recursion and extra work contribute equally to the total time. Because of this balance, a logarithmic factor appears in the final time complexity. Case 3. This case occurs when the number of subproblems and the work done at each level are balanced. Both recursion and extra work contribute equally to the total time. Because of this balance, a logarithmic factor appears in the final time complexity. Example 1. Step 1. We write the recurrence in standard form. And we take an example. In that a is equal to 4, b is equal to 2 and k is equal to 1. Step 2. Comparison decides the case. A is equal to 4, b power k is equal to 2, here 4 greater than 2. Therefore, a greater than b power k. There it satisfies the case 1 condition. We can see an image of case 1 condition. Final conclusion. Log base b into a is equal to log 2 into 4 is equal to 2. Therefore, T of n is equal to theta of n square. Step 1. Merge sort recurrence. Merge sort divides an array into two halves, sorts them recursively, and then merges them. Its recurrence relation is T of n is equal to T of n by 2 plus n. Here, a is equal to number of subproblems. B is equal to factor by which size decreases. F of n is equal to n cost of merging.
In this presentation, we will understand case 2 of the master theorem, which is used to analyze the time complexity of divide and conquer algorithms. The master theorem is used to solve recurrence relations of the form T, n equals at n slash b plus f, n, where we compare the function f, n, with n raised to the power log base b of a. This example falls under case 2 of the master theorem, where the function f, n, is equal to theta, n log n. In such cases, the overall time complexity becomes theta, n log n.
Example 3. T of n is equal to 3t of n by 4 plus n. Therefore, a is equal to 3, b is equal to 4, k is equal to 1. Here, b power k is equal to 4, that is greater than 3. It satisfies case 3. We can see in image beside the case 3 condition. Time complexity is T of n is equal to theta of n. Applications of Master's theorem. Used in analysis of algorithms. Binary search. Strasson's matrix multiplication. Closest pair problem. Karatsuba's algorithm. Advantages. Direct and fast. Avoids expansion and substitution. Works for most divide and conquer recurrences. Thank you.